Hi, everybody. Thanks for choosing to be here now. I know this is an action-packed half hour across the rest of the conference, so glad to have you here. As you heard today, I'm going to talk about fine-tuning LLMs at scale for secure multi-tenant generation, which is a mouthful, but we'll go ahead and break that down as we go. My name's Trevor. I've been a machine learning engineer at Workday for 4.5 years now, let's just go ahead and dive into it. We're going to talk a little bit about Workday, ML at Workday specifically. We're going to talk about really the motivator for what we built here, the quest that we are on. I'm going to share the solution that we built and provide even some lessons that we learned throughout the process so that you all can benefit from those as well. So, ML at Workday. You might be thinking, what is Workday? Workday being a business-to-business company, we sell to plenty of other large companies. If your employer has not decided that they want to own or use Workday, then you've probably not interacted with them unless maybe you've applied for a lot of jobs. Our customers include 60% of the Fortune 500. That gives us about 65 million users. We process almost 1 trillion transactions a year, and we are one of the largest software enterprise software companies in the world. That's just to say that we do a lot of business-to-business stuff, and there are lots of places where we can invest in machine learning to make everybody's day-to-day lives running their businesses easier. There's a lot of opportunities for us to automate tedium. That's effectively like what running a business is tedium. We can help companies grow faster. We have some statistics on the 60% of the Fortune 500 that are our customers have grown faster than companies who did not adopt Workday. We can simplify interfaces. We can make it easier to perform tasks, streamline processes. There's tons of places where we can invest in machine learning. So just a little aside about Workday's tenants. We have a tenanted architecture. We have many different customers. When I say the word tenant, you can think customer. Think some other business out there in the world that has decided to use Workday to manage their enterprise resources. We have on the order of tens of thousands of tenants. And an important aside is that we don't own our customers' data. While it lives in our systems, they are the ones who own it, which means that we are a data processor, not a data owner. And this has, of course, reflected in a few ways in the architectures that you'll see in a little bit. So what's our quest today? We're going to figure out how we at Workday manage enterprise-grade large language models. So we're all here because large language models are really hot right now. And as we heard this morning in the keynote, they can be kind of hard to work with. There's so many moving parts. The stack is really deep. It can be very complex, complicated, however you want to look at it. It can be really difficult to get started. And we were feeling this pain at Workday. Specifically, we would have teams that could take almost 2 weeks to just have an LLM booted on a cluster in a way that they can start training. And many people were writing the same code over and over again. There's a ripe opportunity to consolidate and make an easy-to-use platform that we can share with lots of people. So these are our general enterprise-grade requirements. It needs to be secure, obviously. It needs to be scalable because we're getting new tenants all the time. The data is always getting bigger. It needs to be cost-effective. Workday likes to provide machine learning at the core of its product and in as many opportunities as possible without charging a premium to our customers to use this. So if we can release a new ML-powered feature for every customer and it's viable for us to do that from a cost standpoint, then that's a major win for us. And of course, easy to use. We want this LLM platform end-to-end to be easy enough to use that anybody can pick it up and get going. Because that means that we can create more features, more people can generate value for Workday as a company. And through a bunch of initial research, we realized we wanted to use LoRA. So I'm going to go through a quick refresher on what LoRA is in case you're unaware. You can see here on the left, we have pre-trained weights. This would be a base model that you might pull off the shelf. Llama 3.2, 3 billion model that just released last week, say. Well, to fine-tune a model like that for some other particular use case, you might not want to fine-tune all of those parameters. 3 billion parameters is still a lot. When you start looking at a 70 billion parameter, it's even more. So we're leveraging this technology that came out of Microsoft research some time ago called low-rank adapters that enable you to train just that, an adapter. This is a separate set of weights that can be added on top of a model and provide a small fraction of the parameters in total, but shift the model's behavior enough to make it better at some specific task. So Workday, we might want to train a model to better write job descriptions. In order to do that, we can leverage a LoRA adapter. This then takes the foundational language information from the base model and sort of directs it towards generating job descriptions. So you can see how this might play out at the end here. Every single tenant that we have can have their own adapter with their own information baked into there, in a way that basically makes this large language model work specifically for them. And we can scale these independently with different tenants. So as you can imagine, not all of our customers are the same size. We have some smaller companies that use Workday. We also have some of the largest companies in the world with hundreds of thousands of employees. And so the usage of any particular model in our system is going to shift with the size of the tenant. If we use adapters, we can, of course, scale more granularly to adapt here. Now, all of this is made easy by VLLM. I just want to throw a quick plug in here. They've been having lots of talks at this conference as well. Definitely check them out. They make using many different LoRA adapters dead simple. So, our solution we call Aviato. And if you've seen Silicon Valley, you might be thinking, my Aviato? Well, sorry, Ehrlich, this is not your Aviato. But we do like to have fun at Workday. We thought that this was a fun name to pick. Luckily, Aviato had a successful exit, so we were setting ourselves up for success here. Our Aviato looks a little bit like this at a conceptual level. Our users are going to prepare their data. They're going to run a fine-tuning job. They'll then want to play with their model, especially with large language models. You may not have a really nice evaluation metric. You might actually have to engage with it to get a sense of how good it is. So you're going to evaluate it, and at some point you're going to want to promote it. And you might be thinking to yourself, Trevor, this sounds a lot like machine learning. And that's the point. We want this to feel exactly like any other machine learning somebody might do. Get your data together, which, let's not forget, is the most important part of any machine learning project. Kick off fine-tuning. If this is just as easy as you might think, start fine-tuning. Great, let's see how it goes. Play and evaluate and move on. So what we started with was a script that we pulled from the Ray repository. Number 4 here, fine-tuning LLMs with deep speed. We knew deep speed was quite capable of spreading models across multiple nodes, and we were interested in being able to leverage many small, cheap nodes because getting the bigger ones can be very difficult, as we also heard this morning, especially the hottest GPUs now. There's a lot of contention out there. So if we can find a way to stitch together a whole lot of smaller, easier to acquire instances, that gives us a leg up. About 4 to 6 weeks after we pulled this example off the shelf, we had something that looks like this. This is the Aviato architecture as a whole. So let's go ahead and break it down a little bit and see how each of these components fit together. So as a user, after preparing your data, of course, that's not a very interesting part of this picture, so we're leaving it out. You would go ahead and submit your job. This job would land in our Aviato web service. This is effectively the ingress to our system that can help to then manage all of the other things that are going on within it. And in this case, what we're doing is we're queuing a job up into our Dagster job orchestration queuing system in the background. We use Dagster for a few other logistical things within our ML training ecosystem. So this is an easy way for us to then automate training later in a number of different ways. But you can think of it here as really just a queue to make sure that we're never requesting too many resources at once by only processing a certain number of jobs at a time. Next up is the actual job execution itself. And this is where these individual Dagster job pods will pop open a Ray job cluster. So using KubeRay, you can submit a custom resource definition that describes the cluster you'd like to have to run your training. You send that to Kubernetes, and the KubeRay operator spins up an entire cluster for you to specifically run just your job. When it's done, it shuts down, and that's it. So AnyScale provides some nice ways to wrap jobs for you. We basically just did that ourselves. So we have ways to monitor these jobs to make sure that they're running, collect the logs, make sure that all of this stuff is easy to then find and debug later in case any errors occur. These jobs then all individually interact with an S3 bucket, sort of the team bucket where any particular team would put their data. These jobs then also read that data out of the bucket, and then they save the artifacts at the end of the day back to the bucket. Pretty simple. The Aviata web service here also provides the ability for users to check ongoing logs that we can pull from the Dagster system and fetch some detailed status information that we write in a custom JSON blob format to S3 to make it easier for us to provide fine-grained information for our users on where their jobs are at any particular time. Once fine-tuning is complete, of course, an adapter then will land in the team bucket. And this means that we have to provide some way for our users to play with this. Since it's not feasible to have users pull up their own machine, boot a base model, load an adapter on top of it on their own, we of course built this into the system. And this is where we start to leverage a lot of the auto-scaling capabilities of a Ray serve cluster. So users submit a request to the Aviata web service and say, hey, I'd really like to run my model over here. We can detect which base model that requires. We can boot that base model up. We can grab their adapter out of S3, and we can load them all together to provide them with whatever they want. I'll talk about this in a little bit, but the nice part is after they're done using it, we can detect that they haven't sent any requests in about a half an hour, and we can shut it off. And we can send those GPUs back out into the cloud because we're not using them anymore. Finally, when a user decides that it's time to ship, it's very easy. They can just send off a request and say, hey, that model that I had, it's ready to go to production. We can package it up appropriately and pass it off to our production model store that will then make sure that it gets delivered to the production system for use by our customers. So how does this solution then help us to provide security for our tenants? The first way is how we've structured each individual deployment. So as you can see here, every deployment here runs in a Kubernetes namespace that is specific for the team that is going to be leveraging the compute within there. Now, any of our users here are able to use a role that's been defined to access their data in their team bucket. So we propagate that role to the Kubernetes namespace and all of the resources that run in that namespace as well. But then you might say, okay, well, if the user's living outside of this namespace, how do you make sure that they only have access to the namespace they should? In this case, we leverage AWS's private certificate authority, which allows the user to use their credentials to acquire a certificate to prove that they should have access to this cluster. And then the cluster can validate their credentials, their certificate, against the certificate authority at the ingress, which is just an application load balancer. And now users don't have access to clusters they shouldn't, because those clusters then may have access to data that the users shouldn't. And this sort of separates it all. Now with a little bit of network isolation within the Kubernetes cluster itself manages to make sure that we don't have any bleed between any of the particular roles in our system. At inference time, we can prevent leakage between customers by having trained a customer-specific LoRa adapter. So you've probably heard tales of Samsung employees putting sensitive documents into ChatGPT and somebody else effectively getting them right back out. This prevents all of that from happening because any particular tenant's information is only in their adapter. The base model knows nothing about their specific data. So in this way, we can provide guarantees that For any particular tenant, we know that this request is coming in for that tenant. We can load specifically that tenanted adapter, and we don't have to worry about any transfer of information across, which significantly reduces stress when it comes to training these large language models for a lot of the things that we use them for at Workday. Okay, how does this then scale? Well, I mean, we're using Ray, so obviously that makes it pretty easy. The cluster size scales seamlessly. KubeRay makes this very easy, both for scaling the cluster and for scaling the number of clusters that we're using. You can see here, I have an image that I pulled from Argo where we have a jobs, the head node of a cluster, and it's pulling in 4 more machines that it needs to do its job. And we don't have to touch any of this at all. Completely seamless. We've found that experience to be just super slick. And the number of deployments that we have is made easy by typical infrastructure as code flavored things. So we use Terraform, Argo, you can use whatever you want to repeat this deployment as many times as you want. So we have any number of teams in any number of different regions. Like I said, we operate around the world. A lot of times the data that we're dealing with needs to maintain residency in a particular region, the EU say, and some teams may not want some deployments in some regions, and all of this is very easy for us to manage because the entire deployment is self-contained and can scale on its own. We currently have about 50 of these in production. Maintaining them has not been a headache, so we think that this is working out pretty well for what we need. We also find that the deployment patterns that are made possible by this architecture are very flexible. So on the left here, you can see what it might look like for development. We can run the entire stack on a single machine. This makes it very easy to iterate quickly in a very simple setup. There's also the option, and the one in the middle is effectively describing what I was showing you before, where many users have access to one consolidated but auto-scaling deployment. But because it's so easy to deploy, it's also easy for us to stand up personal clusters if people want to really dig deep into the code, build out different approaches to fine-tuning than the ones that we've already created, or entirely different job types altogether. Then they have an easy way of doing that, also backed by auto-scaling if they desire. So we've alluded to some of this stuff so far, but let's dig into what makes this cost-effective as well. The big one is that we can scale to meet demand, and we can scale back down again. So the whole system is designed to idle with about 2 to 3 CPUs, maybe, and that's maybe a little over-provisioned. So all of the expensive machines, GPU machines, all of that, we don't need any of them to sit there and wait for a user to submit a job. Once a user submits a job, we can scale up. You can see here the blue dotted line is showing total cluster capacity for one of the clusters. Scale up seamlessly to 32 GPUs at times, or even more, and then eventually scale back down when we realize all of the work has been done and we don't need them anymore. When it comes to LoRA, this is a little bit more of a nuanced cost savings. It makes training considerably cheaper. Like I said before, LoRA is a fraction of the tunable parameters of a full model. So you can speed up your job in multiple ways. You need fewer GPUs to be able to hold all of the different states throughout training. And it doesn't take as long because you have fewer weights that you need to update every single time that you make a pass. When it comes to inference time, this also amortizes the cost of a base model. So like I said before, we have different sized tenants. Some tenants just aren't big enough to saturate a base model. So if we were doing a full parameter fine tuning on a base model, there's no way we could make full use of that model for every single tenant that we have. This allows us to group tenants together on top of base models in a way that we can actually see the economy of scale by grouping them together. Now, of course, nothing's a free lunch. The effect of using LoRa adapters will decrease your throughput or increase your latency at about 10 to 20%. This is even a disclaimer on the AnyScale platform as well. They mention that they see this same outcome. But we find that the additional cost here really is far outweighed by the benefits that we get from tenant isolation and cheaper training. And finally, easy to use. This is what it might look like to use the Aviata platform. We publish a Python SDK or client library. You can simply import a few nice classes and build yourself a training job out of this. You submit the data that you'd like to train it on. You can provide an updatable template to change. Maybe you want to train based on different prompts. Maybe you want to train with different base models. You simply change your configuration and ship this off. But we also subscribe to this concept of progressive disclosure, in that it should be really easy to get started, but if you feel like you need a little more control, it's all still there. So here you can see a much more complicated configuration where you can submit, you can decide how long you want your max sequence length to be, pick special tokens, you can describe everything you want about your trainer, your cluster size, there's a ton of configurations available to you here if you felt like you needed to, although our sensible defaults do pretty well for most of our users. So, since we've got plenty of time here, let's go ahead and talk through some of the lessons that we learned along the way. In particular, they boiled down to one thing, and that is that this wouldn't have been an issue with per job clusters. That's a quote from me. My team, of course, was sick of hearing this for quite a while. I remember being here a year ago and hearing per job clusters were the way to go. But when I got started on building this project, it was more difficult. I was going to require Kubernetes. I would require KubeRay at hand in order to spin up a per job cluster. And developing on a single machine was just a lot easier given the infrastructure that we had at the time. So I started with that, one single auto-scaling cluster. And here I'm going to share a quick illustration of one of the ways in which we found that this was suboptimal, so that maybe you can remember why it's important to go ahead and start with per job clusters. So imagine this. You have a job. You'd like to run it on 6 different machines. A job just finished. You have 2 of those machines. They're in your cluster. They're healthy. They're ready to go. Reporting great. This next time step, the Kubernetes autoscaler has managed to bring 3 more machines in. They're getting booted up, added to the cluster. The 2 that you had before are still hanging on just fine. But that last one, it's been a little harder to source. It just isn't quite there yet. Now, in this next step, those 3 machines that were just added, they're reporting healthy. We finally found that 6th one. Everything's great, except the first 2, Ray has realized, have been sitting idle for a little while. And because you have the auto-scaling settings say, after it's been idle for some number of minutes, let's go ahead and kick this node out. Well, now they're getting kicked out of the cluster. Luckily, they're still part of Kubernetes, so it doesn't take them long to come back. But the problem is, they have a little bit of time that they take to boot back up again. And this can stick you in an infinite loop of trying to balance a whole lot of machines at one time. So especially if you're dealing with 16 nodes, 32 nodes, like I said before, we like to stitch a bunch of cheap instances together. Single GPU nodes, we can train across 32 of them, but not if we can't get them all started at the same time. So you have to change your autoscaler settings a little bit, say, hey, a little longer of a timeout before we go ahead and kick them out of the cluster. And this gives us more time to make sure that everything aligns. There's also a few other nuances here that I'd be happy to talk about if people are curious about those. But so far what we've covered is what ML looks like at Workday to some extent, how we put together a system that helps us to support enterprise-grade large language models that is cheap to run, secure in both the training and the inference side, and scalable in many dimensions, and how we learned the hard way that per job clusters are the way to go. So thank you very much, and we'll go ahead and open it up for questions. What do you mean by that? Providers. Yeah. So the question was, are there any specific Kubernetes providers we're using? We chose the Kubernetes foundation because of the fact that this can run on any Kubernetes provider. Specifically, we use EKS, but that is effectively neither here nor there. One of the major benefits with this is that we could eventually adapt all of this code to run on TPUs. We could leverage Google Cloud. We could put it onto Azure just as easily. Everybody provides Kubernetes. It's a great way to make whatever it is that you're building cloud agnostic, we'll say. Yes?
For the LoRA approach, is there a limitation about what's the size of the data for each one that it can hold?
Yeah, so there's some, back of the envelope calculations there. People have a few rules of thumb. We find that if you have on the order of 1,000 to 3,000 samples, and you run, 2 to 3 epochs over your training setup, you can do pretty well. Because there aren't many parameters to tune, we find that they converge relatively quickly, and generally speaking, don't require a ton of data to actually adapt to the task that you're trying to tune them for. We've done a bunch of experiments on LoRa versus full parameter fine tuning. There's actually been a bunch of AnyScale blog posts about this, and in most cases, LoRa is sufficient. Unless you're really trying to adapt a model like deeply in its ability to reason about something, might you need full parameter fine tuning. But again, as generally consumers of a lot of this tech and applying it to these specific tasks that we need, we find that many of the other people in the world, Meta, will release a new model with considerably better capabilities before we would be able to fine-tune one ourselves on our own internal data. And so having the ability to, refine any one of these particular models for a specific task is proving to be enough for what we need to do. Yeah. Yeah, so the question is whether or not one base model can rule them all, basically. We've had a strong gravitation towards the Llama 3 series. The 8 billion instruct models seem to provide us a pretty solid foundation for most of the things that we care to do. We also need to run big embedding workloads or things like that, in which case there may be additional other models that are more suited for that specific task. But for most of the things that we want, we find that the Llama 3 series, even the small ones, if they can't do it out of the box, they can absolutely do it with fine-tuning. Yeah?
So you started the talk talking about your data processing, not data owners. So how do you approach kind of training your base models?
Yeah, so we pulled the base models off the shelf, and then we just train these adapters. When it comes time to, or I guess when we're sort of in production, we will generally retrain these things every 2 weeks or so, because that's sort of our keep data fresh expiration policy limit, which means that we will expire an adapter. We'll get new data that we can extract out of the tenant to sort of refresh the source. We'll run that through training to pop out a new adapter, and then we can ship that adapter into production, and then just sort of keep that cycle running week over week.
Are there separate adapters for each customer?
Yeah. Yep. Yeah. So that's where it really starts to scale out. This is where the so separate adapters for each customer. Having that Dagster queuing orchestration layer really helps us to both kick off jobs when we detect new data, new tenants, new whatever, and also make sure that we aren't trying to do too many of them at the same time, because that may just be asking for too many resources from the cloud at any one point. So, yeah. I think we had a question over here first. Yeah. Sorry.
Could you share more details about your observability stack and some of the hard lessons learned from that?
Yeah, sure. So at Workday, we run an in-house Prometheus observability stack. Ray and, Ray specifically ships with excellent Prometheus interoperability. So we basically just tell Prometheus to scrape the metrics from the cluster, and they all show up. Ray provides dashboards in Grafana that give you good observation of Ray serve, compute resource usage, all of that kind of stuff. So we actually had a really easy time getting that set up. Yeah, and then.
This is a follow-up on the previous question on fine-tuning the model using your latest data.
Mhm.
Have you considered RAG implementation to get?
Yeah.
What are the challenges?
The question is RAG. That's a whole different presentation. We do leverage RAG for a number of our features as well. But of course, we find fine-tuning and RAG solve different problems. So if you want to talk more about that, we can do that because I think we're at time. So thank you, everybody.